Yeah, I would like to welcome everybody to the Western Hemisphere Colloquium on Geometry and Physics. This is our second time we're doing this. We have our Zoom room here. I'd also like to welcome our participants watching on the YouTube live stream. I have on the screen here some guidelines that we'd like the participants to follow to make this work smoothly with so many participants. We will have everybody except the speaker will be muted during the lecture, but you can still ask questions by using Zoom's chat feature. Our moderators are moderating the chat. They will aggregate their questions and will pass them on to the speaker as appropriate during the talk. After the talk is over, we'll have a question and answer period, and you can use Zoom's raise hand feature to be called upon to ask questions of the speaker. When the moderator calls on you, please don't forget to unmute yourself. And the talk will be 1 hour and with a 15-minute question and answer afterwards. So it gives me great pleasure to introduce today's speaker, Kevin Costello from Perimeter. His title is Topological Strings, Twistors, and Skyrmions.
Okay, Kevin, thanks very much, Charlotte. Let me just, there we go. Great. Okay, so I hope my slides are now visible. So what I want to talk about is a new project I've been working on for the past couple of months. And so it's kind of work in progress. There's a lot to be done, lots I don't understand. But on the other hand, I'm quite excited about it. So I thought it would be fun to prepare and talk about something that I'm pretty excited about for this meeting. And what I want to talk about is a variant of the twistor string theory that was introduced many years ago by Witten and Berkowitz. So in their story, the twistor string theory was used as a description of n equals 4 super-Yang mills in 4 dimensions. So the twistor string theory I introduced today will instead describe a non-renormalizable theory, which is the sigma model on the group SO8 in 4 dimensions. So the sigma model and group models and group manifolds were studied many years ago by Skyrme. So these models are often called Skyrmion models. And so as we will see, that the sigma model on the group SO8 has some very surprising and to me fascinating properties, which are explained by its origin in twistor space. In particular, we'll see it has a kind of integrability reminiscent of the familiar integrable 2-dimensional theories, in particular the principal chiral model. So I'll start by reminding everybody a little bit about twistors. So maybe not everybody is quite as obsessed with twistors as I am. So it's a beautiful subject introduced by Penrose many years ago. There's a lovely paper of Tia and Hitchin as well, which is very important in the topic. So the twistor space I'll call it PT, is it's simply the fibration O-1 over CP1. Now the way to think about it is every point in CP1 gives you a complex structure on OR4. So CP1 is the set of complex structures in OR4 compatible with a certain orientation. It's the coset SO4 modulo U2. And as I vary over CP1, I get a fibration of OR4s, each with their complex structure, and this is the fibration. This is the total space of that fibration. Now, because of this, the twistor space as a smooth manifold is in fact a product. It's a product of CP1 and OR4. So there's a fibration from the twistor space to OR4. I'll call the twistor fibration. And the fibers are CP1. So what Penrose realized many, many years ago is that holomorphic PDEs, things like the D-bar equation on twistor space, become familiar SO4 invariant PDEs on OR4. For example, one of the basic examples is that the collection of harmonic functions on OR4 is the same as the first chief cohomology of the twistor space with values in O-2. So this example will be important later. But if I change O-2 to some other line model or some other sheaf on twistor space, on this other side, I'll change my PD in some way. So this has been well studied, and there's many examples of that nature. So in that vein, a field theory on twistor space, which is holomorphic, by which I mean, roughly speaking, that the kinetic term is given by the d-bar equation, should give you some kind of ordinary field theory on OR4. For example, if I want to write down a field theory on twistor space, where the field configurations are related to H1 of O-2, I should have a gauge field. So if I take a gauge field, which lives in omega 0, 1, twisted by O-2, with this Lagrangian, A d bar A. By the way, can people see the mouse, Sheldon? Is the mouse visible? No?
Yes, it's perfectly visible.
Okay, good. Thank you. So this Lagrangian, if I study the equations of motion, of course, the equations of motion modulo gauge will be H1 with coefficients in O-2. And that suggests that once I dimensionally reduce from twistor space to OR4, this Lagrangian becomes the free massless scalar. And that is indeed true. You can check it. It's kind of fun to check it by choosing a gauge where on every twistor fiber, A is in the kernel of d bar star, and then you just calculate what this Lagrangian becomes, and it is this. Now, there are many, many more examples. Perhaps the most famous one is essentially due to Penrose and Ward. Well, they didn't phrase it in this way. I learned about it from a nice paper of Michael and Movchev and some lovely papers of Bowles, Mason, and Skinner. Is that holomorphic BF theory of twistor space is equivalent to self-dual Yang-Mills theory. So self-dual Yang-Mills theory is a very simple theory. I just introduce a Lagrange multiplier, forcing the gauge field to have self-dual curvature. So it's much simpler than ordinary Yang-Mills theory. Now, Witten and Berkovitz, some time ago, suggested that one should study the topological B model on a super twistor space. And what they found is that, when we studied the topological B model, the theory on a brane is holomorphic Chern-Simons. And they found that holomorphic Chern-Simons on super twistor space is equivalent to the self-dual limit, this is important, of n equals 4 Yang-Mills. So of course they wanted to study the full n equals 4 Yang-Mills, but if we simply put holomorphic Chern-Simons in twistor space, we'll find this self-dual limit. So these examples suggest there's kind of a problem. Well, not a problem, but anytime we try to build a theory on Euclidean space by starting with a holomorphic theory on twistor space, we find something kind of boring. If we start, our first example gave us a free scalar field. Our second example gave us self-dual Yang-Mills theory, which is almost free, not quite free, but it's 1 lib exact, doesn't have any scattering. It's much more boring than full Yang-Mills theory. Now, the most interesting example is the n equals 4 case. Well, if we just start with holomorphic Chern-Simons theory on twistor space, then it was realized in Witten's and Berkowitz's original papers that you do not get n equals 4 Yang-Mills. What you have to do is to modify it by adding on non-local terms. Those non-local terms arise because really we're studying a string theory and not a field theory of twistor space. So from the point of view of Witten and Berkowitz, those are D1 instantons. And I recommend this paper of Bowles, Mason, and Skinner, who wrote down a lovely formula for exactly which non-local terms realize the correct action of n equals 4 Yang-Mills. So let's move on to say a little bit about what I want to study today. So I'm going to study a new variant of the twistor string theory. So this will be a local field theory on twistor space, simply some version of holomorphic Chern-Simons theory, a little bit different than the one studied by Witten and Berkowitz. But we'll find, because we're working on twistor space and not super twistor space, that the corresponding field theory in 4 dimensions is not supersymmetric at all. It is simply the sigma model with target the group SO8. So, and as I said before, the fact that this sigma model comes from twistor space will tell us some remarkable features of this 4-dimensional theory, which I find, which is what excites me about this topic. So let me try to say a little bit about what the field theory on twistor space I'd like to introduce is. So the field theory it's called holomorphic Chern-Simons theory. So this is a simple Lagrangian field theory you can write down on any Calabi-Yau threefold introduced by Witten. It's a theory that lives on a brane in the topological B model. And the field is a Gage field, which is just a 0-1 form. So it's describing a holomorphic G bundle. And the Lagrangian is I simply wedge the Chern-Simons term, the Chern-Simons Lagrangian, with the holomorphic 3-form omega. This is a very simple Lagrangian. However, of course, I want to put this in twistor space. Unfortunately, twistor space is not Calabi-Yau. The twistor space is an open subset of CP3, so its canonical bundle is O-4. Well, to solve this problem, we have to take our volume form, omega, which enters the holomorphic Chern-Simons Lagrangian, to have second order poles at 0 and infinity. It needs to have a total order of pole of 4, and here I put 2 of them at 0 in CP1 and the other 2 at infinity in CP. So that in coordinates, it looks like dv1, dv2, dz mod z squared, for instance. Here is z as a coordinate at CP1 and vi coordinates on the fibers, the O-1 squared fibers. So I'd like to study holomorphic Chern-Simons with this volume form. However, that doesn't really work if you're naive about it, because if you think about the Gage transformations that appear here, they involve applying d bar to the Gage transformation. Normally that would be 0 because by integration by parts and the fact that d bar of omega vanishes. In our situation, omega has poles, so d bar of omega does not vanish. And this Lagrangian is not Gage invariant. It turns out to be easy to fix. What you need to do is ask that the Gage field vanishes at 0 and infinity, and also that the Gage transformations are the identity there. If you do that, the zeros in the Gage field and the Gage transformation cancel out with the poles, and you get a perfectly nice Lagrangian. And what we're doing really is we're defining elliptic boundary conditions, Dirichlet boundary conditions for our holomorphic Chern-Simons theory at the locus z equals 0 and z equals infinity. Okay, so are there any questions so far?
I have received no questions.
There have been no questions so far.
Okay. So we can ask.
The questions are coming in if you still want them.
Sure, yeah, if there's a good question, go for it.
So one question is whether your Gage transforms are the same as changes of coordinates.
No, the Gage transformations are just the usual ones on any G bundle. So I'm done here. The standard Gage, the same kind of Gage transformations you would find in Young-Mills theory.
I guess that's the only question so far.
Okay. Okay, so we can ask, we have this theory on twistor space. What is the resulting effective field theory on R4. So to think about that, we must remember that a point of R4 corresponds to a CP1 inside of twistor space. And in 6 dimensions on twistor space, my field is a holomorphic G bundle. That's the equations of motion of holomorphic Chern-Simons theory. Well, even without imposing the equations of motion, if I take my 0, 1 form and I restrict it to this P1, it defines a holomorphic G bundle. But because I ask my Gage transformations to be 0, to be the identity at 0 and infinity, it's a holomorphic G bundle trivialized at 0 and infinity. Now, under some mild genericity assumptions, every holomorphic bundle on CP1 is trivial. So by comparing the two trivializations at 0 and infinity, it's kind of like a parallel transport, but a holomorphic version of a parallel transport. We find that the data of my 6-dimensional field is exactly an element of the group. And this element of the group further catches, if I apply a Gage transformation to A, I will get the same element of the group. So this field sigma captures exactly all of the Gage invariant information I had in 6 dimensions. So whatever I started with in twistor space, the resulting 4-dimensional field theory will be a sigma model from R4 to my group manifold. So before going further, we might think of a very simple case. Suppose my group was just U1, or even better, it was OR. It was just the rank 1 abelian group. Then A is a 0, 1 form twisted by O minus 2. And we know that corresponds to a free massless scalar in 4 dimensions. And that's what we're seeing here, a map from R4 to the group, which is OR. So it's a scalar field. So far what we've done is compatible with the familiar story of Penrose from many decades ago.
I have a question, Kevin.
Yeah.
So can you use any Gage group, or do you have to use UN/N?
Classically, you can use any Gage group. There's a one-loop anomaly which forces you to use either SO8 or UN/N, depending on if you're doing type 1 topological strings or the ordinary topological strings. So for me, SO8 is the interesting case. Well, so I did this. This is a little quick. Yes, what is the Lagrangian? But this turns out to be not that hard. And well, I had a recent paper with Masahiro Yamazaki about computing understanding 2-dimensional integrable field theories from 4-dimensional Chern-Simons theory, which is a little bit analogous to this. And if you do a calculation identical to a calculation in that paper, we'll find that this is a Lagrangian. So the first term, so here J is the current for the sigma model, so it's sigma inverse d sigma. So the first term is just the standard kinetic term associated to the invariant metric on G. And the second term is a little bit funny. It's a Weissymino term, but it's a Weissymino term in 4 dimensions, where I integrate over a 5-dimensional space of the trace of the cube of the current times the Kähler form. Well, if you look at this Lagrangian is almost the same as the Lagrangian for the 2-dimensional WZW model, except I'm doing a 4-dimensional integral instead of a 2-dimensional integral, and I've thrown in the Kähler form to make the forms of the right degree so that I can integrate them. And the relative coefficients are the same as the ones you find in the WZW model. So I won't give you the details of this calculation. It's really not hard. And as I mentioned, it's compatible with in the case of an abelian group, which is the case studied by Penrose. We just have this term giving you a massless scalar field. This term is funny though, and I'd like to explain how to understand it. So, well, here's the slide, just repeats what I just said. So this is some 4D analog of the Weissman term. Oh, and I should point out that Lorentz invariance is broken. I mean, not broken, it's broken to a copy of SU2. Well, if we think back, that's not that surprising because the Lorentz group acts on twistor space, but it rotates the CP1, whereas we've chosen a form which is not, we've chosen a 3-form of twistor space, which is not invariant under the rotations of that CP1 because it fixes as a divisor at 0 and infinity. So of course we have to break the Lorentz group. So let's move on to understanding of this term. Unless there's any more questions.
Yeah, there are a couple of questions. Let me relate them.
Okay.
So one question is, what Kähler form are you using on R4 cross R plus?
Sorry, that was unclear. The Kähler form is the Kähler form in R4, and it's independent of this extra variable.
Okay. So that was from Edward Witten. Ezra Getzler is asking, why isn't the group G complex?
Ezra is correct that the group is complex. I was sliding over this point. So what we're finding is an analytically continued theory with a complex space of fields where the path integral has to be done over a contour. Now, because I'm really working in perturbation theory, so the choice of the contour doesn't matter. To describe the full non-perturbative theory, a careful analysis of the contour would be necessary. So for work on analytically continued theories, one can look at Edward's paper on quantum mechanics and the A model. It's kind of in the same vein.
Do you want more questions, or are you?
Okay, I mean, maybe I'll move on for now then. Okay.
Go for it.
Yeah. So how do we understand this funny term? Well, I think there's a nice understanding of it in terms of some topological symmetries of the 4D signal model. So people might be familiar with the fact that 2D signal models can have states which are charged under the vortex number, which happens when your circle, if you have a target, which is non-trivial fundamental group, you can have states associated to circles which wind around elements of pi1 of the target in a 2-dimensional signal model. So there's something similar in 4D. This group manifold has non-trivial pi3, and there's a corresponding third cohomology class, which looks like this on G. And that class can be thought of as giving a U1 symmetry for the 4-dimensional signal model. And this expression here is the current. And all we're doing, this funny WZ term, is we're coupling to a background gauge field for this symmetry, because we can rewrite it as a 4-dimensional integral where I have a U1 gauge field A whose curvature is the Kähler form. So this expression here, by integration by parts, is equivalent to the expression I wrote previously. So from that point of view, it looks a little less weird if you write it like this. We just have a background U1 gauge field for this funny symmetry. And I could just remind readers, there's this really fun story of the Skyrme model, which I actually don't know much about, but I think it's kind of interesting, where this symmetry plays an important role. This is supposed to be an effective field theory for QCD, where the group is SUN. The field sigma is the exponential of the mesons, like the bilinears of the quarks. You have this topological U1 charge, and according to the Skyrme model, that's supposed to be baryon number. So this is just to point out that this U1 charge is a familiar object in some areas of physics. Okay, so we can ask, but classically, seeing that holomorphic Chern-Simons theory in twistor space gives you a single model with target G. So let's turn to Davide's question, which is, does this work for every G at the quantum level? But it turns out no. So at the quantum level, holomorphic Chern-Simons has a one-loop Gage anomaly. So that one can calculate this in many ways, for instance, using the index theorem. But what you find is that this diagram with 4 external lines is not Gage invariant. And the Gage variation of it is this expression here, where C is the parameter of the Gage transformation. Well, it turns out that sometimes you can cancel this Gage variation by introducing closed string fields. So this cancellation is this topological string version of the famous Green-Schwarz mechanism in the 10-dimensional string. So the closed string fields, it's a 2-1 form in twistor space with log poles on the divisor at 0 and infinity. I'm not going to go into too much detail about these closed string fields. I'll be pretty quick about them. And this couples, if A is the field of holomorphic Chern-Simons, the closed string fields couples in this way. So know that A is a 0-1 form, alpha is a 2-1 form, so this whole expression is a 3-3 form. And this expression here is the kinetic term for A. So this kinetic term was introduced by Bershadzky, Sigati, Ugurian, and Vafa many years ago. And we noticed there's something very funny about it. It has a del inverse in it. And that only makes sense because del alpha is 0. But despite this kind of very strange thing, you can still play the usual Feynman rules with this Lagrangian. You can write down a propagator, so on and so forth. So what C and I showed is that if the group is SO8, then introducing these closed string fields will cancel the anomaly. So let's see why that's the case. So we saw that this diagram gives rise to an expression which looks like the trace of the Gage variation parameter times del alpha cubed. So this expression here gives rise to a similar expression. So here we have the closed string propagator. So on each, because the closed string propagator, the closed string field is coupled by a trace, we're going to have 2 traces. And this is what we find. So these 2 things will cancel as long as the trace of x to the 4th is proportional to the trace of x squared squared. Now it's important that this trace is in the adjoint representation. This trace up here is in the adjoint representation. For this one, it doesn't really matter what representation you take the trace in because they're all proportional to each other. So some algebras this happens, some it doesn't. It happens for SO8. It also happens for SL2 and E8 and a couple of other things. But for SO8, we can show that all anomalies on all orders in perturbation theory cancel. And that the quantum theory is uniquely fixed. So from the point of view of the worldsheet, what we're studying is the topological B model. We target the twistor space, but it's unoriented. So it's just like the type 1 string in 10 dimensions. It's a type 1 topological string. Okay, any questions then?
Actually, yes, Ezra here. Can I ask, since nobody else is asking? So your field alpha, so if I think of it as a Kodaira-Spencer field representing a deformation of the complex structure on PT, so what's its logarithmic behavior? In what way, what structure, extra structure is it in fact a deformation in the correct sense of the Calabi-Yau, logarithmic Calabi-Yau structure?
It's a bit funny. So if you turn it into a Beltrami differential, then the Beltrami differential So it vanishes when restricted to the divisor. So that is, it preserves, it's like the identity vector field on the divisor. So it preserves a set of coordinates on the divisor. And it also preserves a normal vector to the divisor. So I don't quite know what that means. It describes deformations of PT with two divisors with some coordinates and a normal vector. It's a little funny.
Okay, thanks. Okay.
Kevin, there's a question from Greg Moore.
Okay.
Can you take an orientifold in this construction?
I know when people do the type, do the A model, they study orientifolds. So I am. It seems reasonable that there's some chains of T-dualities might lead you to orientifolds here too, but I don't know. Well, so let's so let's compare to the story of Witten and Berkowitz. So they did the ordinary B model on the super twistor space, CP3/4, which is Calabi-Yau, unlike the twistor space we're considering. They found that there was rated to n equals 4 angles. Here we're taking the B model, the ordinary twistor space, but the type 1B model, and it's going to be related to the signal model with target SO8. Okay, so what does the twistor story buy us? Well, the claim, so this is the part that gets me kind of excited about this story, is firstly, the origin from twistor space will give us good control over the org flow and over possible counterterms in this theory. So I find this quite remarkable because it's a non-renormalizable theory in 4 dimensions. So normally at the quantum level, that's a big mess because you can choose all, there's an infinite number. As you go further in the loop expansion, there's more and more counterterms you can include. But the claim is that if you want to be consistent with the twistor space, we still have good control over those, and those are fixed. We also find by studying other brains that has some hints of integrability, and it has a Laxed Matrix. And finally, certain correlation functions seem to emit good analytic behavior. So these features make me think it's an interesting 4-dimensional theory to study. So I'll first discuss this point here, how we have good control over the counterterms of the org flow. So to do this, we need to understand how the org flow works from the point of view of twistor space. Just on OR4, the org flow comes from the action of positive reals by rescaling. So on twistor space, that action simply comes from rescaling the fibers, which are O-1 squared, like the fibers of this twistor projection from PT to CP1. Now, obviously, that extends to an action of C star. Now, that's kind of a triviality, but it implies something really remarkable. If you take any theory, like any local field theory of twistor space, the org flow is periodic in the imaginary direction. This is kind of a strange property. It almost never happens. So let's write that out more carefully. If I take lambda to be the log of the scale, then T of lambda is the theory at scale lambda. And let's imagine analytically continuing this where lambda is a complex number. Then the periodicity we're discussing says T of lambda plus I is equal to T of lambda. And this takes place in the world of analytically continued theories, right? Even if I start with the real value of lambda as an ordinary theory, for this to make sense, I have to move into the analytically continued world. But this really strongly constrains possible divergences in the theory. Now, if I had a logarithmic divergence, say epsilon is a cutoff, then this could not happen because T of lambda would have its dependence on lambda would come through log lambda. And that's the kind of thing we're excluding. Things cannot depend on the logarithm of lambda. So it excludes any logarithmic divergences. So this is really strange. I mean, this almost never happens. If you give me a random Lagrangian, say normalizable or not, it will always have log. It will almost always have log divergences. For instance, the interacting scalar field theory cannot come from twistor space because, as a local quantum theory on twistor space, because it has log divergences. And four-dimensional Yang-Mill similarly cannot come from twistor space. Okay. Any more questions? Or?
There have been a lot of questions about why SO8. So Andy Knightsky is asking if it's possible for the anomalies also to cancel higher loops for other groups like E8. Do you know that they don't?
Okay, that's a really good question. I don't know that they don't. I also don't know that they do. Another good source of evidence for why this should happen for SO8, or SO8 should be privileged, is that this type 1 topological string can be embedded in the physical string in type 2b with 47s and an 07 plus or minus plane, I forget, one of the two. So this is similar to the way the ordinary topological string can be embedded in the physical string by turning on this gravity photon background. Now, so in the physical string, it seems like you have, in that setup, you really need SO8, and I don't know other brain configurations that you can join to an 07 minus plane to give you other groups. So that seems to be another argument for why SO8 is privileged. But yeah, I'm not entirely sure.
You explicitly use triality? That's a question from Johnson Fried.
No. I don't use triality explicitly. My understanding is that I want to introduce D1 brains at some stage, and to introduce D1 brains, I'll need to break the triality symmetry. So the triality of this model is related to the S-duality of type 2b. So I mean, string theory experts can help me here. So, yeah, but I don't explicitly use triality.
Thank you.
Okay. So we can ask how is it possible that this theory can have a periodic orgy trajectory given it's such a strange phenomenon? Maybe let me pause to emphasize what a strange thing this is. I mean, if you took some dynamical system, some manifold with a vector field, and we analytically continued it to a complex manifold with a holomorphic vector field, it would be extremely rare for a trajectory to become a cylinder. Most trajectories would just become, some kind of little strip or something like that. This is very non-generic behavior. Okay, so how could this possibly happen? So to answer this question, let's just try to write things down and check, are there any log divergences? We try to calculate, and we find that only for SO8, there aren't any. And there's some funny Green-Schwarz mechanism thing that cancels them. So let's see how this works. So to do this, I'm going to write my field, choose a field phi, which is the log of sigma. This is a field which lives in the Lie algebra. I'll write things in terms of this field instead. And then my Lagrangian becomes just the usual scalar field for that guy. And there's another term which looks like phi del phi d bar phi times the scalar metric plus higher order terms. The higher order terms are quite complicated because this current J is a complicated expression of phi. So it turns out if I ignore the higher order terms, exactly this Lagrangian was studied in some lovely work by Sasha Goncharov, who was interested in so this Lagrangian somehow reproduced some mixed Hodge structures. I don't fully understand it. In any case, so let's look at this Lagrangian. It turns out there is a one-loop logarithmic divergence given by this diagram, the same diagram we studied earlier. So you can convince yourself of this by looking at the dimensionality, just by considering how many propagators we have and the dimensions of the propagators and how many integrals we're doing. You can convince yourself this looks like should be a log divergence of this form. Okay, so just the sigma model on G, it looks like it does not have this strange feature of a periodic orgy flow. But fortunately, this log divergence seems to be cancelled by some closed string fields, just like on twistor space, the anomaly was cancelled. So there's a very similar mechanism, and the way it goes is as follows. We have to study what do these 2-1 forms become when we take them down to real space, to 4-dimensional Euclidean space. Well, we find this 2-1 form with log poles becomes an anti-self-dual 2 form and a scalar. Well, in 6 dimensions, the Lagrangian was kind of weird. It had like this del inverse thing. So I don't want to write a Lagrangian. So I'm just going to write what equations these fields satisfy and what the 2-point functions look like. Because that's all we're going to need. So I'm really kind of describing the algebra of operators. So they satisfy this equation, d bar plus star d gamma is 0. This is an elliptic equation. And the 2-point functions, the important one is that bb is the radius to the 4th power. Where here I've contracted all the 2-form indices in the SO4 invariant way. And the way they're coupled is, well, the original Lagrangian depended on a Kähler metric. All I do is I vary the Kähler metric. So this is kind of what we would expect, because from the 6-dimensional point of view, these fields control the deformations, certain deformations of complex structure, compatible with the divisors at 0 and infinity, as in the question that Ezra asked. So it's not surprising that they're kind of gravitational in some sense. Okay, so why did they cancel the log divergence? We look at this term. bb is the radius to the 4th power, 1 over the radius to the 4th power. And we look at how they're coupled. If phi is log sigma, I get a term like this, del phi, del bar phi b. And since this guy is order to the -4th, I put 2 of them together. Well, I'm doing an integral, you see. So I'm integrating in 4 dimensions, 1 over order to the 4th, that has a logarithmic divergence of the same kind, but now I take del phi, del bar phi squared. Well, the original divergence I found had trace of del phi, del bar phi, del phi, del bar phi. And these have a chance to cancel as long as some Lie algebraic identity holds, which is the same one we found earlier that holds for SO8. Okay, so this kind of sketch that, I mean, I must admit, I haven't done every detail of this calculation. I've done this part of it, but there's also coupling to the scalar field. I haven't gone through that in full detail, but this at least suggests that what we found, the anomalies we found in 6 dimensions translate into log divergences in 4 dimensions, and the anomaly cancellation becomes cancellation of log divergences. Okay. Any questions about that story?
There was a question from a minute ago from Martin Rorschach.
Yeah.
He's asking whether the SO8 is the same as SO8 in Gage and equals 8 supergravity.
I have no idea. I mean, if that's related to this story with the 07 minus plane, possibly, but other than that, I have no idea.
Another one from Greg Moore.
Hmm.
He's suggesting that in statistical mechanics, whenever you analytically continue time, and you work at finite temperature, you always get periodicity. So
I didn't know that.
can you compare?
Didn't know that, so there's something I can say about it. I'll have to think about that.
I guess you can talk with Greg about it.
Yes. Okay, so I mentioned, this signal model is non-renormalizable. So that means normally it's a big mess. You can't really talk about the quantum theory because there's too much ambiguity. So from the 40 perspective, there's infinitely many possible choices of the counterterms. But if we want to have it make sense as a 60 theory, that's much harder. So in the 40 perspective, there's loads of local counterterms I can build. But it's much hard. I mean, very few of those will be realized as 60 local counterterms. If I give you a generic 40 expression, that will be realized as some non-local thing in 60. So we already saw this in the study of n equals 4 Yang-Mills, where one of the terms in the n equals 4 Yang-Mills action was a non-local expression in 60. So if I want to realize that as a 60 theory, that's much, much harder, and there's many fewer possibilities. But if we also want to ask that all the anomalies cancel in 60, that's even harder. And C and I, this kind of general story, which applies to in this case, there's some cohomological cancellation, which means the 60 counterterms are just fixed by anomaly cancellation. So this is probably too ambitious, but one could fantasize that in 40, the counterterms are fixed by the requirement that the orgy flow is periodic. Because if you add on a random counterterm, that will spoil that property. That certainly constrains it. If you were hopeful, that might constrain it very strongly, but I don't know that. So the other thing about this theory that I'd like to discuss is its integrability. So there are many people who are familiar with two-dimensional integrable models. And these are characterized by the fact that they have a Laxed matrix, L, which is a holomorphic function of some parameter Z called a spectral parameter. And this is a one form, which it's an operator valued one form of the theory, and it satisfies this flatness equation. So in other words, classically, the equations of motion are going to be equivalent to this flatness. At the quantum level, it's better not to talk about the Laxed matrix. It's better to talk about its path-ordered exponential along some line. And well, this expression here, flatness, translates at the quantum level into saying that this path-ordered exponential is a conserved quantity. So this tells us that these two-dimensional integrable theories have an infinite number of non-local conserved quantities. And in more modern language, it's better to think about this conserved quantity as being a topological line defect. So what happens in 40? So there are some arguments, I forget who they are due to, possibly Edward, that if you have Lorentz invariant theories in 4 dimensions, it is not possible to be integrable. But fortunately, we've broken Lorentz invariance a little bit. And it turns out we do have something that looks a little bit integrable. So what do we have? The claim is that this model has a Laxed matrix, L of Z, but it's going to be something a little bit different than what we've had in 2 dimensions. The L of Z is a 0-1 form in O4 in complex structure Z. So as I move Z, what kind of tensor I have changes because Z parameterizes a complex structure in O4. And for every value of Z, this satisfies the Laxed equation, the d bar of it in that complex structure plus the commutator vanishes. So it's very easy to check this at the classical level. We simply compute the equations of motion, which I didn't do before. The equations of motion are a linear equation of the current. And then my Laxed matrix is just the projection. I take this, I have a special complex structure for 0 and infinity. I take the projection onto a 0, 1 form from zero, and then I further project onto a 0, 1 form for z. That's my Laxed matrix. And the fact that it satisfies this equation follows in these very simple equations of motion. And from the more conceptual point of view, it's obvious we have such a thing, because all I do is I take my 6-dimensional gauge field on twistor space, and the Laxed matrix is its expectation value. Because the 6-dimensional fields tell us that this is the 0,2 curvature of this vanishes, that implies the Laxed equation. So, in fact, the argument I've just sketched tells us that any theory coming from a local field theory in twistor space has a Laxed matrix of this form. Now, what happens at the quantum level? This Laxed matrix, because it's a 0, 1 form of this complex structure, it's something we can couple to chiral fields which live on a surface, but that surface can't be arbitrary, it must be holomorphic in this complex structure. So we get a family of surface defects. Like, so for each z, I get some possible surface defects which live on curves holomorphic in complex structure z. But another feature of the Laxed equation, so in the 2-dimensional case, the Laxed equation told us that when I vary my path ordered exponential, the charge didn't change. So here we have something similar, but because the Laxed equation is of a holomorphic nature, this tells us that the surface defect doesn't change when I vary its position. Sorry, that the surface, I take that back. The surface defect depends holomorphically on the position of S. So let's write that out in more coordinates. And we'll see that this will lead to having an infinite number of conserved charges. Let's take our 4D spacetime to be a 3 torus times r. Well, we've made 3 directions periodic. The whole twistor story works too. We can make it periodic as well. Now, for countably many complex structures, this will look like an elliptic curve across C star. Let's choose such a complex structure and choose U to be a coordinate on the elliptic curve and V on C star. Then I have a surface defect which wraps the elliptic curve and V. And this surface defect is holomorphic as a function of V. So we all know how in a 2D theory, if we have a holomorphic operator, we get an infinite number of conserved charges. We just form its contour integral. Similarly, here, I take the contour integral over the unit circle in the V plane, and this is a conserved charge, and I have an infinite number of them. In fact, infinite in 2 ways. For each z, I have this integer k. Further, z can take on countably many values. If k is equal to 0, all of these operators commute. So let's see why that's true. On the twistor space, these surface defects come from D1 branes, which are 2-dimensional holomorphic objects, which live in the fiber over a point in CP1. If I put 2 D1s at different points, different values of z, they just don't touch each other in twistor space. Although in real space they intersect, or they can intersect in real space. So because they don't touch each other in twistor space, I can move them past each other, and these operators commute. Therefore, their averages also commute. So in this way, we found an infinite number conserved and non-local charges. Okay, so maybe pause there for questions again.
Well, there was a question from Jacques Disler. I tried to unmute him. I'm not sure if he's there.
Oh, sorry, Jack. Sorry.
I'll ask it later
Okay.
in the question period.
Okay. Okay, so we're nearly done. So let me just explain what we've done so far. So I've argued that this 4D model with this funny WZW term has a periodic ordeal trajectory, has a well-defined quantization, and has infinitely many commuting non-local charges. There's another, I want to mention what seems to be another nice feature of this model, which I must say I don't really understand very well, which is that certain correlation functions appear to have a quite controllable analytic behavior. So to remind you, so one of the beautiful things that came out of the ordinary twistor string theory was that scattering amplitudes were understood in terms of the geometry of algebraic curves in twistor space. So here we're going to find something similar, but for correlation functions instead. How does this work? So we can insert a D1 brane in this topological string theory. And let's take a D1 brane, which I call vertical. That means it wraps the CP1 twistor fiber. Well, the theory on the D1 brane, if you calculate it, it's turns out to be the symplectic bosons on this holomorphic symplectic manifold M, which can be described either as the minimal nilpotent orbit of SO8 or the space of charge 1 instantons for SO8. Now, at 0 and infinity, we have to choose some boundary conditions. So the boundary conditions are given by Lagrangians in M. So because this vertical D1 brane it lives at a point in real space, becomes a local operator. We can describe it as follows. If I assume that these two Lagrangians intersect at a point, then SO8 acts by some Hamiltonian functions on this minimal nilpotent orbit. You can calculate that the local operator looks like the exponential of the Hamiltonian functions evaluated at this point in the manifold times phi. And that this is just the leading order, and then there's some kind of quantum correction to this, which I don't understand. Okay, so whatever these local operators, whatever the full expression of these local operators are, for purely formal reasons, we can see that they have very special analytic properties. That is, so imagine we can define the correlation functions by choosing some state at infinity. Normally, these would make sense for x in OR4, x is the position of the operators. But here, because the operator was something I defined using a copy of CP1 in twistor space, the correlation functions depend holomorphically on the choice of a CP1 in twistor space. The collection of CP1s in twistor space is C4. So we conclude that the correlation functions analytically extend to functions on n copies of C4. So that's really surprising. There's no branch cuts or anything like that. But further, well, on C4, it's like, when can these correlation functions have possible singularities? Well, because they're defined for curves on twistor space, the only way they can have a singularity is if those two curves intersect. When two curves on twistor space intersect, corresponding points on C4 have the feature that the difference is null. So we conclude the correlation functions are some meromorphic function on C4 with poles are like this meromorphic function on a bunch of copies of C4 with poles on the locus where 2 points are differ by a null vector. So that seems to be quite a strong constraint to me, and hopefully would allow one to get your hands on them. In particular, it implies that there's an iso B, because meromorphic functions, if I just fix one operator at 0, and I consider the other one, this is a meromorphic function on C4 with the pole along the divisor given by the null vectors. And such meromorphic functions have a nice expansion. So this suggests possibly one could use things like the bootstrap to understand correlation functions. Okay, so this is everything I have to say. And as I said, lots of things are very preliminary, but I'm quite excited about it. And I'll stop there.
Thank you, Kevin. Great talk. And I invite questions using the raise hand features in Zoom. That would be in your participants menu. If you'd like to raise your hand, I can unmute you and call on you. Oh, I saw there was.
I have a question. This is Samson.
Hi, Samson.
How are you?
Good.
Listen, there is something very, very long ago, Greg Moore, Nikita Nekrasov, Andrei Losev, and I called four-dimensional Weizmann-Witten model, which has a motion written in terms of the Young's parametrization. So I used to call Young's equation for self-dual Young mills. When you solve the holomorphic lattice condition and write everything in terms of the remaining last equation. Anyway, so Manin or someone very long ago, maybe it was Ed Witten, I'm sorry, I don't remember, wrote the solutions of this Young's equation in a twistor space where everything is described holomorphically. And your equation of motion that you wrote in 6 dimensions, the twistor equation with U and W bar, have that solution that Manin wrote, this holomorphic kind of Riemann-Hilbert problem solution for the 4-dimensional Weizmann-Witten equation. So I think that what you are describing is how to say, holomorphic way in 6 dimensions to describe 4-dimensional Weizmann-Witten model, which is sigma mod. Now, what I'm missing a bit, I am not sure I understand what is SO8, why SO8 is special there, because that theory was scale invariant. I mean, it's a long story, if you might remember. I just want you to comment that there might be relation, and maybe Greg can say something. I think Greg is here.
Thank you. Thanks, Samson. I'm afraid I'm not as familiar with that paper as I should be, but clearly I need to go read up about it. But just maybe if Greg has anything to say about it.
Samson and I have been exchanging messages saying, hey, this looks like that. Hey, that looks like that. So there seem to be a lot of points of, at least that are reminiscent. So in particular, we talked about things called algebraic sector, an algebraic sector of exact correlation functions. Based on, I guess they would be called now surface defects associated with a divisor in the Kähler manifold. So the idea was very simple. You take a Kähler manifold and you wedge the WZW action with the Kähler form. And then there were special one-loop renormalization properties. I don't remember anything special about SO8. There was certainly a relation to twistors, and there was something we called the holomorphic sector. So anyway, there's some points of similarity.
No, absolutely, yes. Well, thank you for putting that out. Was your model supersymmetric or not?
It was not.
I see.
It also had some relation, what we call the 4-dimensional Verlinde formula, kind of later described by mathematicians, but there are lots of similarities. We just wanted to point out that maybe it makes sense to have.
We have a question from Edward Witten. Or are we done with that?
No, I'll go ahead. So, Kevin, first of all, great talk.
Thank you.
Statement about integrability above 2 dimensions is really due to Wesson's amino. Sorry, to still Coleman and Mandula. And the basic statement is that the S matrix is trivial in an integrable system above 2 dimensions. So you're not contradicting that because you haven't discussed an S matrix, and maybe it turns out to be trivial. I believe Sampson's probably right that your equation of motion in 4 dimensions can be viewed as Yang's equation.
Mm-hmm.
Well, except that Yang would have had a Hermitian matrix, whereas you've got an element of the group, of the Lie group. So it's a little different. But anyway, Yang's equation was related to instantons and thereby to twistor theory in a different way. I don't know exactly how it's connected to what you're doing. My main comment, though, was that, okay, integrability suggests that your model, if we try to make sense of its S matrix, would turn out to have a trivial S matrix.
Did the arguments involve Lorentz invariants? I mean, were they?
In a rather weak way. The basic argument is just the following. Consider one particle states. Then if there are any conserved quantities other than usual ones, how can they act on one particle states? All you can really do to one particle state is to act on it with a function of its momentum. Or in your case, the one particle states are in the adjoint representation of SO8. Well, it can also depend on the SO8 quantum numbers, but roughly it's just a function of the momentum. And then you find that if you have conserved quantities that are non-standard functions of the momenta, that makes it impossible to have non-trivial scattering. I don't understand your setup well enough to be sure that the logic will apply in your setup.
Right.
Okay. The fact that your correlation functions are rational, if I understood properly, kind of also tends to suggest that that's correct. It's actually a little bit unnatural in your setup to try to define an S matrix because it's a Lorentz signature concept, and your setup is more natural in Euclidean signature.
This is true, but other people have some understanding of how to relate twistor space and Lorentzian field theories. I find that very confusing because it involves a correspondence, but.
Well, there are different things that are done. One is that twistor space can be interpreted in 2-2 signature, but that is again not that natural as home for an S matrix. Yeah, okay. Okay, I'm not sure what you have in mind as a way to get to a Lorentz signature from twistor space. It's much easier to get to 2-2 or a 4-0 signature.
Mm-hmm.
Okay, we're done with that. We have a question from Lucas Stepien.
Thank you very much. And can you hear me?
Yes.
Yes, we can hear you.
Fine. And I have a question concerning Bogomolny equations, namely whether there exist analogons of Bogomolny equations in the case of field theory in twistor space. This is one question. And the second question is as follows. Namely, there is an analogon of Derek-Hobart scaling argument in the case of field theory in twistor space, because I'm not a specialist in twistor space. I'm interested in usual field theory, classical field theory, scalar field theory, Young Mies and so far and so far. So this is my question because this is very interesting for me, and thank you.
Well, I'm not sure. The Bogomolny equations involves D and D star in 3 dimensions. If we try to apply to holomorphic Chern-Simons, you can imagine an equation involving D bar and D bar star. But that would be a bit funny for me because it wouldn't really be. It would depend on more than a complex structure in twistor space. It would depend on a Kähler metric on twistor space, and I felt I would spoil lots of things that I like about it. So I don't think that there's a. I don't know of a nice Bogomolny equations on twistor space. And for your other question, You said, I didn't quite catch it. You said about a Hubbard model, was it right?
Yes, please repeat because I'm not sure. Please repeat your.
Well, I didn't quite catch your other question. Were you asking about a Hubbard model? I didn't quite.
No. My second question.
Mm-hmm.
My second question is as follows about the Derek-Hubbard theorem, because this is very well known fact that a simple example, if you have scalar field theory, classical scalar field theory, this is very well known fact that there do not exist any non-trivial solutions, localized solutions with finite energy for the case in dimensions bigger than 2. And this is so-called Derek scaling argument or Derek-Hubbard theorem.
Yes.
And whether there in the case of field theory in twistor space is such analogon of such theorem.
Probably, because that kind of result just involves scaling and dimensional analysis, and you can certainly scale on twistor space. For instance, for the sigma model on the group manifold, Skyrme introduced another term to bypass that kind of thing. So it's true, if you were on flat space and you just took the sigma model I wrote down, there wouldn't be any, I can't imagine any very interesting solutions on R3, possibly, but studying things like radial quantization would be a different matter, though.
Okay. Thank you very much. Thanks a lot.
Thank you.
Jacques, did you want to ask your question now?
Yeah, I did. So if you do the ordinary nonlinear sigma model in 4 dimensions, forgetting for a moment about the Wessel-Mino term, there are 2 Lorentz structures with a log divergent coefficient at 1 loop. And I have only a vague idea how things work with your Green-Schwarz field alpha. Does it cancel both of those or just the one you wrote down?
So this was the point where I said I hadn't done all the calculations in as much detail as I should have. Let's see.
I mean, so in principle, there are even more possible counter term structures in this non-Lorentz invariant theory, but I know there are at least 2 in the Lorentz invariant version.
Well, let's see. I mean, everything at 1 loop is dimensionless.
So for instance, the 2 I would see are the things where you have del bar del bar and del bar.
Right. Okay.
And then possibly other things with 3 del bars and 1 del and stuff like that. But those might vanish for
those. I think the symmetry reasons will exclude those.
Right. But at least there are at least 2 staring at you just from that term by itself.
That's right. I don't remember. I feel at some stage I thought about this, and are they not related by total derivatives?
No, I don't think so.
I think so.
I think they're really independent, but I could be misremembering.
Okay, no, I'll have to. This is I know this is like the kids are home from school and I mean, on the closed string side, I only calculated one of the 2 possible diagrams as well. So
right.
What happens is that the other diagram cancels the other anomaly. So I really need to go check that carefully.
Okay. Thanks.
Mm-hmm.
Are there any other questions?
Well, I'd like to comment on what on Jacques' thing. So in the WZW4 case, which I think is similar to what Kevin's doing,
Yes. Mhm.
they were surprising one loop cancellation.
That sounds very similar, yeah. But you didn't, it seems funny to me you had the surprising one loop calculations without a kind of Green-Schwarz thing.
That's one of the differences. There was some discussion of a relation to Kodaira-Spencer theory, but I don't really remember anything about it.
Okay, so I clearly need to read your papers very carefully.
Are there other questions or comments? Okay, hearing none, let's thank Kevin again.
Thanks.
Thank you all for coming.